Good morning. I'm glad you're here on the last day of school before spring break. A couple interesting transitions. It's going to be fun to have everyone come back on the same day after spring break and to be in the classroom a full 4 days a week. I wish it was five, but I think four is a good start. Today we are not actually going to do the next section in our textbook. I want to kind of consolidate some things. I built a fairly large Delta Math assignment. It says it'll take about 40 minutes, and I want you to watch this too. Uh, First idea I want to talk about is that if we have an inequality that's obvious to us, like for example, 2 is less than 7, right? Okay, we understand that that's true. And if I think about it, like I've got the number 2, right? The number 2, and I've got the number 7. And it looks like this. Like the 2 is smaller than the 7. If I take those numbers and I add 3 to both, right? If I kick both up by 3 units, they get bigger by 3. It becomes 5 is less than 10. Okay? Now, the first inequality was true, right? It is always true that 2 is less than 7. And when I increased both by the same amount, right? I had unequal things and I added the same thing to both sides. I got another inequality that was also true. So a lot of these ideas play out. It turns out that if you have an inequality, you add the exact same thing to both sides, you get a new equivalent equality that is also true. If you have the 2 is less than 7, and on both sides of that, I took away 3, right? If I subtracted 3, this would become a -1. Less than this would become a 4, right? It is true that -1 is less than 4. So addition and subtraction present no problems in terms of the truth of an inequality. Also, it's the case that if you have an inequality and you multiply both sides by positive integers, you get an equivalent true statement. So you get a statement that's also always true. So for example, when I say 2 is less than 7, if I double both sides, I get that 4 is less than 14. 4 is less than 14. That's always true. So we have yet another equivalent inequality. So that's fine. We do have a problem, however, if we take an inequality, and let's go back to our 2, 2 is less than 7, and we multiply both sides by a negative value. And it doesn't matter if it's a fraction less than 1, like we're dividing, but if we're multiplying or dividing something by a negative value, it changes the truth of the statement. So just real simply, on both sides, if I multiplied both sides by -2, this would become a -4, and this would become a -14. Now you can see what happened. By multiplying by the -2, it's like I swung everything around on the number line, and now the smaller item is not the one that's on the left-hand side. The smaller item is the one on the right. So this is the case, right? -4 is greater than -14. So I want you to be aware of that. When we see inequalities, a lot of times we can treat them pretty much like equalities, but there's this instance shows up. Now, earlier when we first introduced solving inequalities, our thought was this. We're going to have this and we're going to find something called a boundary location. Once we know the boundary, we're going to test and see which side of the boundary works. That works really well for us. So if I take this, I could say, okay, I want to find the boundary. That means I'm looking for where 3x plus 2 is simply equal to 5x plus 6. I could take away 5x from both sides and get -2x plus 2 is 6. I can subtract 2 from both sides. -2x is equal to 4, and then I could divide both sides by 2. I get that x is -2. So my boundary location is apparently the number -2. So if I draw that on a number line, here's my number 0, here's -1, here's -2, it's a boundary. Because this was less than or equal to, I know that that is a closed boundary, but because it includes the or equal to. So on this, I would put a closed dot indicating that -2 is part of my solution. And then I would just test. I would test the number 0. And when I put 0 into my original inequality, right, when 0 goes in for x here, and when 0 goes in for x right here, I clearly get that 2 is less than or equal to 6. I get this. I get the statement 2 is less than or equal to 6, which is always true. So I know that the points on this side, are making the inequality true. So it turns out that my answer is -2 and everything larger than -2. Now, we're pattern recognizers, and a lot of us do a few of these, and we start to see, oh, it just seems like I just have to look at this, right? If it's less than, I'm going to go to the left. If it's greater than, I'm going to go to the right. The reason why I want you to be aware of this idea of getting the boundary and testing is because that's clearly not the case here. Now, I'll explain why that's not the case. It's not the case because of what we just talked about over there. But my solution here is x is anything that is greater than or equal to -2. So an alternate approach to that very same problem would just be aware of the fact that my properties of equality largely work the same way with an inequality, with the exception that if I multiply or divide both sides by a negative number, the direction of my inequality has to flip. And I'll just remind us of this idea. If I have 2 is less than 5, that's true. If I multiply both sides by -1, so I'm going to multiply both sides by the value -1. When I do that, I get a -2 and I get a -5. Who's bigger now? You're bigger now, right? So that multiplication by the -1, right, flip things around and the direction of my inequality switched. So let's look at this problem. Let me move it just over here just a little bit. That's better. So I'm going to take the exact same steps that I did previously when I was finding the boundary point. I'm going to subtract 5x from each side. That's going to make this a -2x plus 2 is less than or equal to 6. Now I'm going to take away 2 from both sides. I've got -2x is less than or equal to the number 4. And now I'm going to divide both sides by, -2. So I'm either dividing by -2 or I'm multiplying by -1/2. But because there's that division or multiplication by a negative value, the direction's flipping. So when I divide this side by -2, I get x. When I divide this by -2, I get -2. And look out, the direction of my inequality flipped from what it originally was. So you can see that that's pretty much exactly what we mirrored on the other side. And you can see we ended up getting the green inequality here, that x's were greater than or equal to the number -2. So both methods are fine. I just want I want to encourage you that even once you get an answer like this, I would say, let me pick a number bigger than -2 and just check it. So if I pick a value that's bigger than -2, like 0, and check it, it should make the original inequality true. If it doesn't, there's an issue. A couple more things I want to talk about. This is a compound inequality, and we've seen that these are the types of things that we get when we're solving absolute value inequalities. Not exactly, but similar. So these are joined by the word or. So when we have things that are joined by or, it's going to be either stuff on one side or stuff on the other side. So to solve this compound inequality, I'm just going to solve each part independently and realize that at the end, things are joined by or, and that I could graph the solution. So on this first side here, I'm going to subtract 10 from both sides. That gives me that -x is greater than or equal to 6. And now you can see it, there's a negative there. So I have to multiply both sides by -1. So I get that x's are less than or equal to the number 6. Okay, flipped it. On the other side, I've got this or here, and I've got, I guess I'll take away 10 from both sides. That's going to give me a -8 is greater than -x. A -8 is greater than the opposite of x. Again, I'm going to multiply both sides by -1. When I do that, this is 8, and this is now an x. And because I multiplied by the -1, the direction has to flip. Now, on this particular compound inequality joined by or, not both boundaries are included. So if I was going to graph this solution, right, this saying, hey, here is the number 8, and it says 8 is not included, but x's are those things that are greater than 8. So x's go off this way. And then I have this one that says, hey, x's are less than or equal to 6. So here's the number 6. And x's are those values that are less than or equal to it. So that's why at 6, I'm putting a closed boundary indicating that 6 is included as a solution, and my solutions are simply all those things that are 6 or smaller than 6. So this is my solution region. Now, a thing I could do is I could test some values like 9, or I can test a value like -5. And because this is an or statement, one of those two things above would be true, right? If I test the number 9, it should make this inequality true. And yeah, if I put a 9 in here, the opposite of 9 is -9 plus 10 is -1. 2 is greater than -1. So this values, this side satisfies this half of the inequality. And because it's an or statement, only one of the two conditions have to be true. So things either there are true or the things are there. However, if I pick a number like number 7, neither one of these are going to be true, right? An or statement, either this one or both, but in the case of 7, neither would be satisfied. One more thing I want to look at, and that's this one that's joined by and. When we get our solution for and, I mentioned this in class yesterday, you can join this together as one big equality or big compound inequality without the word and in it. It's just important that when you do that, you start with the smallest number and then your x and then your larger bounds. So if I was to solve this real quickly by taking away 5 from both sides, for the first part, this would become 3x is greater than 6, therefore x is greater than 2, and it also has to be true for this entire solution that 3x has to be less than 32 minus 5, which would be, what, 37? No, 27? 27? Take away 2, take away, 27. And then divide both sides by 3, I get that x's are less than the number 9. So this is an and statement. Both parts have to be true. If I was going to think about this on a number line, here's the number 9. It is not included as a solution because this is an open boundary, so it's strictly less than. Over here we've got the number 2. This is also not included. But you can see what this says. It says x's are those things that are greater than 2, but they are less than 9. Greater than 2 and less than 9. So that's the solution region only. That's the region where both things would be satisfied, right? Both this inequality and this inequality are true here. Now the way you can write your final answers, you can simply say, oh, here's the number, oops, not with a green pen. You can say, here's the number 2, and then I've got my x's, and then I've got the number 9. And this just nicely says, hey, x's are those things. X's are those things that are between 2 and 9, not including the endpoints, not including 2 and not including 9. All right, we're at 13 minutes. I hope you have fun wrapping up today's math assignment, and I look forward to seeing you in April when we're all back together. This is Mr. Roberts. Have a great day.